at least for our community, is can we describe tissue using tools and methods that are standard in statistical physics? So can we describe them in terms of a glass transition or a geometry transition, or these kind of approaches? And of course, we would like to understand what are the control parameters, what is controlling this, their behavior. And also, we know that tissue are not standard thermal system, so we would like to understand at the microscopic scale what is unique, what is actually making tissue a living system. And there are different approaches to this question. So in the biological community, what has been done, and this has brought a lot of insight, is the so-called top-down approach. I will call it learning by breaking. So to understand how a biological system works, what you usually do, you go there and you perturb. You suppress the expression of a gene, and you see what is the consequence on a microscopic individual to understand what is the role of the gene. Another approach, which is more physically inspired, is the top-down approach, in which you try to build models. And this has become extremely popular in the community in, perhaps I can do from here, in the last decades, mainly because we have been, we had a very important advancement from the experimental viewpoint. So we are now able to image tissue with a very high spatial resolution. And so we know where cells are, and also inside the cell, the dynamics of the cytoskeleton. We have more recent insight about the mechanics. It's now possible to measure, at least to have insight on what are the forces between the forces between cells. So for instance, now we know that tissue most often are under a state of tensile stresses. And then from the theoretical viewpoint, we had a lot of insight from non-equilibrium physics, in particular from the branch of active marker. So if you want to try to make a model of tissue, you have to think of what are the basic ingredients, and the basic ingredient is, of course, the cell. What is a cell? A cell is, from the physical viewpoint, is a colloidal scale particle, which, however, is not rigid, is actually deformable. So you need to think about, okay, is the deformability important? If so, how many degrees of freedom I need to use to describe this deformability, and how I use them practically. And then you want to discuss the dynamics, and you know that the way cells move is through the dynamics driven by the lamellipodium. That is, cells have not only a bottom-up symmetry, but a front-back symmetry. And the way they work, they extend at the front part. They extend some protrusion. The protrusion grabs to the substrate, and then the cell pulls itself forward, and so on and so forth. So this is a lamellipodium. So if this is important, if so, you have to think about how to describe. And then, of course, you have a tissue which is a collection of cells. So you have many cells, and the cells are interacting. So you need to describe this interaction, which are mediated by a cell-cell junction. So the typical length of this cell-cell junction is much smaller than the typical size of the cell. So these are kind of sticky particles, if you want. And so you have to describe this kind of interaction. And another thing you have to do is to describe something that I'm going to focus a lot in this talk, which is different kind of sensing. So how a cell is able to sense the environment and to respond to it. So of course, there have been a lot of models that are trying to mimic this kind of behavior. And here I'm just listing a few of them, like the POTS model, where you put cell on, each cell is a collection of sites of some color. So here is the figure just represented one cell. And you can think about some kind of dynamics, which is a very simple model, but of course it's has its limitation when you study the dynamics. So what is time, or you study the elasticity, is very difficult. Or you can have a center-based model, which each cell is kind of Lennard-Jones particle. So you are totally missing the deformability of the particle. So is it important or no? How do you cope with it? On the other side, you have a model like the Voronoi and the vertex model. We have heard about it yesterday. Well, these are not models for cell. These are models for tessellation, meaning that you only have a cell because you have a neighbor. Okay, so you cannot model an isolated cell. If you want to do that, you have to develop a very complicated model. And then I have to say this model have kind of behavior that is difficult to rationalize. For instance, you start compressing this model and they fluidize. So say, okay, perhaps there is something that is not really physical. Or there is a recent addition to the zoology is the phase field model, where you describe each cell as a concentration gradient. This is a very nice model, but computationally they are very, very expensive. So you can simulate just a very small number of cells. And there have been, of course, many efforts to try to mix model or to try to extend this to try to mitigate the limitation. And one consequence of this, somehow, this plethora of models is that there is actually not an agreement on what control very simple basic feature of the behavioral tissue. So for instance, you may want to ask what is actually causing motility and what is actually trying to slow down motion. So there is one thing in which everyone agrees is that the motility is promoting tissue motion. You ramp up the motility and cells tend to move. But then you might think, okay, what is the effect of crowding? So intuitively you may think, okay, I compress the tissue and the tissue the dynamic is slowing down. And you see this in some experiment. This is reproduced by particle-based model, but you also have experiment that are suggesting the converse, and you have models, the Voronoi and the vertex model, that is suggesting that you compress the tissue and the dynamics might speed up, which is a little bit weird. Or you may think, what is the effect of adhesion? And again, you find experiment and some model that suggests what you will say. The first thing you may think of is that if adhesion increases, then the dynamics slow down, particles stick to each other. But it is also found or suggested the converse. And about sensing, we're going to focus on a particular model of sensing, which is called contact inhibition locomotion. So the name suggests you that upon contact, the cells should stop moving. This is suggested by some experiment, by the first experiment that have been introduced in this sensing mechanism. But then you also have experiments that suggest the converse, and when people try to encode these sensing mechanisms in models, they find that it's actually promoting tissue motion. Okay, so there is, on very basic things, there is not an agreement. Let me say that from the model viewpoint, things are complicated, but from the experimental viewpoint, are even more complicated. And the reason is that we like this kind of schematic description, like adhesion, density, or sensing. But experimentally, these are not control parameters that you can tune independently. Okay? So for instance, if you want to tune adhesion, what you usually do, you add some drug that is interacting with the expression of cadherin, molecules in the cadherin family, which are involved in the formation of junction. But the same molecules are involved in the sensing, in contact inhibition. So you perturb adhesion, but you also perturb sensing. So you don't know precisely what is happening. Okay. So what we are going to do here is to try to develop a new model, which I'll say a little bit of subcellular here, and then we move out of equilibrium and we study what is the effect of motility, densing, adhesion, and contact inhibition. And then we're going to focus a little bit on wound healing, and we are going to suggest that it's possible to introduce the concept of force chains also in this kind of soft, squishy particles. So the model that we introduce, we call it Next Tissue. We call it Next Tissue because NTU is the acronym of my own institution, a young technological university, so I have some edge when I beg for money. And it is an extension of LAMPS, so which is a very popular package, and if you are interested, you can just take and download it. And the starting point is related to what we have seen in the last talk yesterday. So it's a model introduced by the group of Corey O'Hare, which is the deformable particle model. So we are in 2 dimensions. And so each particle is described as a ring polymer. So in the energy functional, you have a term here, which is just the sum over all the spring. But then you don't want the polymer to collapse. And then you add another term, which is a penalty related to the dependence of the area with respect to some preferred value H0. Okay? And you can non-dimensionalize this energy functional for one single particle, and it turns out that it depends on, very similar to the Voronoi and vertex models, depends on one parameter. You can introduce P0, which is the ratio between essentially the preferred value of the perimeter, which is the number of bits, and L0 is the typical distance, over the square root of area. And we're going to focus here on a value which is somehow large, 3.9, means that this particle are very squishy. So their individual shear modulus is very, very small. Let me say that the model resembles a lot.
Why is it 3.9 and not 4 and 3.5?
We can change as long as we are soft. above some threshold, that's not really, it's not really important. One thing that I would like to highlight is that this P0 in this model is affecting the properties of a single cell. This is very different from what you have in the vertex and body model, where the P0 combine the property of the cell and the property of the interaction all together in one parameter. Here we have two different things. P0 is property of the cell. How about the interaction? The interaction of the cell, as we mentioned, is driven by the formation of adhesion molecules. And so what we say that between the membranes beads of two cells, we are interacting, adding an interaction potential, which is an attractive potential. So overall, the interaction potential between monomers of different particles is going to be 0 if they're far away, then you have some attraction, and then of course you have repulsion because you don't want interpenetration, okay? The key point here I would like to highlight is that this attraction range is very small compared to the size of the diameter. So the blue is very small compared to the particle size. So we are in the regime of sticky particle. The particle only interact when you're very close, okay? Already with this model, yes, Silke. Yes, we do have problem in which the surface here might buckle. This might happen, but you have to go to very high density. So if the volume fractions don't go to very high, we are okay. We can fix in principle if one essentially following what has been discussed yesterday. So you can add some kind of angular spring to prevent this thing. But we are not going to this high value of the density. So we are not going to. We already have too many parameters. So we try to not to add other things. Okay, so already with this model, you can study very simple things. So this is a very famous experiment by Chara's group, which they grow a tissue on a plate, then they detach it, so you have a suspended monolayer, and then they pull and stretch. So here there is no dynamics, essentially, if you want. It's a quasi-static induced fracture. And in the model, you see possible animation. You can do the same thing. You prepare your tissue, and then you stretch it, and you see you have a confluence tissue that at some point it fractured.
Can you say a little bit about what special features of this node?
Or this one?
Yeah.
So one special feature that is matched in the experiment is that if you look at what is the strain, the elongation at which the system breaks, is large. It's very large. So it's the order of 1 or 0.6 or something like this, which is huge compared to the one of molecular solid or colloid solid. This.
What about gels? I mean,
it might similar to be the one of gels. Yeah. Related to the formability. No, possibly you don't see here. Possibly here there is. So the color cells are in blue when they are interacting. So here possibly you don't see there are the gray cells because these are the free boundary. Okay. So they're here and they are on the left, on the top. I mean the free boundary. Possibly you don't see them, but okay. Or you can do the shearing. This is related to what was done yesterday. So this we start with essentially what was a crystal, and then you shear. You're essentially always confluent, and you see the deformation of the cell, and you're going to see clear emergence of nematic ordering and these kind of things. Okay, but in the talk here, we're not going to focus on the mechanics. We're going to focus most on the phase behavior. So the first thing I want to do is to have a reference.
sorry, in terms of this kind of cell shape change, is that something that's seen in tissue, or it's?
It is something that is seen in model tissue. Yes, there is a lot of discussion about the nematic order induced by deformation. Yeah. Well, they are not actually experiments that they are actually doing this kind of protocols. This is more our style than the biological style. Okay, so the equilibrium phase diagram. So what we're going to do is a very standard thing. So we have a system of 1,000 cells, each of them with 50 monomers. And we apply a stochastic force to the center of mass, and then essentially we do a Langevin dynamics. We ensure that we are in equilibrium, so long enough simulation, and then we characterize the phase. And what do you find for the phase diagram is these things here. So so here we're plotting on this axis the temperature in units of the strength of the attraction between the monomers. So if you are at high temperature and you increase the density, what you see that the dynamics is slowing down. The color code is the diffusion coefficient. And then at some point you enter a glassy regime. You can define whatever you want. Or if you fix the density and you cool down the temperature, you enter in a regime of phase separation. And this is just, for instance, an illustration of what you see in the coexistence line. So one thing that you notice is that you have the coexistence between a very dense phase and essentially an empty gas, right? Which is what you see here. You have the coexistence between essentially an empty liquid and a dense one. Okay, and here let me say that on this axis we have the density, but I'm actually plotting the density in terms of the so-called effective volume fraction, which is the volume fraction the system would have assuming that the size of the particle does not change, remains the one in the dilute condition, okay? If you think about the actual volume fraction, it's bounded by 1. You cannot really go above 1, but this one can go above 1, and 1 is essentially is what you expect at confluence, okay? Okay, so another thing I'd like to notice is that this phase diagram is essentially very, very similar to the phase diagram that people observe in a system of hard colloidal particle with sticky interaction, okay? There are some minor differences I'm going to discuss, but it's very, very similar. So the main message is that the softness is not really inducing a new physics, at least from this point of view. There are some differences, but.
So Massimo, one question.
Where are you? Oh, yeah, sorry.
D is diffusivity, that particle diffusivity. What is D?
D is the particle diffusivity.
Diffusivity.
This is it. Yes. I'm going to comment then on this. Okay, so now I would like to drive the system out of equilibrium to see how things are going to change for the phase diagram. And the first thing that we're going to do, we are going to introduce some motility. Okay, so no temperature, but motility. How do we do that? In the following, we attach to each cell what is the center of mass, and to the center of mass we attach a polarity, n, and then given the position, given the polarity and the position of each monomer with respect to the center of mass, we can define an angle phi. And this phi allows us to identify the monomers that are in front of the cell, which here are some other one in orange, from the monomers that are on the back. So the way we model this lamelliponium-induced dynamics is to say, oh, the active forces are only acting on the monomers that are in front. And we also assume here that the active forces are parallel to R. Another option would be parallel to N, but parallel to R appears more reasonable to us. And there are differences in the typical shape that you get, these kind of things. And then the cell move, and there is, of course, a viscous damping due to the interaction with the substrate. So in terms of parameter, one thing to realize is that when you study healthy cell and you focus on what is the typical velocity and rotational diffusion coefficient for the motion of the polarity, what this gives rise to a persistent length that turns out to be of the order of 1 cell diameter. Okay, so Peclet number is very, very small. For a healthy cell. You can add drags to change this, but for a healthy cell, this is the number you get. So if you study, we're going to study the phase diagram. On one axis, we're going to have the density, and the other one, we have this motile force that we're going to normalize. We're going to normalize with the minimum force you need to apply to detach two molecules, two cells, okay? And this is useful because there are experiments that are studying this and tell us that the typical Hilting force between two cells is of the order of 10 to the minus 7 Newton. So we have a kind of way to relate to experiment. And this is the comparison between the two phase diagrams. This is the thermal phase diagram, and this is the phase diagram just induced by this motility. And what you see is that they are very similar, right? So this is the main message. And why they are very similar, and the reason is very, very simple, because yes, we are out of equilibrium, but the Peclet number is very, very small. The persistence length is 1, so we don't expect, for instance, we are way below the typical persistent length at which you will have motility-induced phase separation in 2 dimensions, okay? So you don't expect important changes, okay? So motility is there, but it's not really key. Okay, so now we're going to discuss sensing, and sensing turns out to be a very important aspect of living matter. So Molecular Biology of the Cell, which is kind of the only text in the community, state that the essence of life lies in its ability to sense the environment, process information, and generate appropriate response. And of course, it's very well known that cells have some sensing ability. One thing that is very well established is that cells are able to respond to gradients, like chemical gradients, or also gradients in the stiffness of the substrate. They like to go towards the stiffer region. Here, we're going to focus on another kind of sensing, so we don't have inhomogeneities in the space, but we're going to study the sensing of the interaction between the molecules. So how a molecule our cell respond to the interaction to another. And we're going to focus in particular on so-called contact inhibition of locomotion. So let me say that many sensing mechanisms have been proposed in the community, but then when you dig down and you ask what is the sensing mechanism that has been experimentally proven, in the sense that is known precisely what is the biological pathways that is activating during sensing and then is causing a mechanical response. Well, this is essentially the only one. There is contact inhibition, then contact of reproduction, inhibition of reproduction. And so this is the reason why we only introduced this one in the model. So how does it work here? Consider the interaction, the collision between two cells. Here are the lamellipodia at the front. So the cell established contact. So here the front junction, they adhere to each other. In response to this, a whole cascade of biological pathways that is activated inside the cell, and the response that you get is that the extension of the protrusion in the direction of contact is inhibited, while the extension in other direction is still there. And so the consequence is that the cell is going to rotate. Okay? So this allows you to resolve the contact. And contact inhibition has been shown to slow down the motion in the suspension of sick fibroblasts. This is what Abercrombie introduced. And Abercrombie suggested that it's actually involved in the cancer invasion, because essentially, since it's inhibiting motion, he said, okay, if you have a dysfunctional seal, then the cell can actually are able to invade. They don't stop their motion. On the other side, since this is a way that cells have to resolve their contacts, it is also expected that it's very useful to promote tissue invasion, because the cell, instead of trying to push towards the neighbor, are going to move toward the free space, okay? Because they want to resolve their contact. They orient toward the free space. So the way we model is to essentially to a non-reciprocal interaction between cells. So consider again the interaction between two cells. Only the lamellipodium is sensing, only the front part. So for instance, in our case, the top cell has a free lamellipodium, so it's not affected by this interaction in terms of the polarity. How about the cell that is below? The cell that is below does not want to extend its lamellipodium in this direction, in the direction of contact, but is still able to extend in the other direction. What is the other direction? This is the direction of the free space probed by the lamellipodium. Okay? So it's not extending the lamellipodium on the back, but it's expecting in the direction of free space probed by the lamellipodium. So what we do, we identify this direction, and then we introduce an alignment interaction between the polarity and this direction, which we define somehow as the direction of the free space probed by the lamellipodium. So when you do that, you need to introduce a typical time scale for the alignment, and also an alignment strength. And the alignment strength is going to depend on the structure, because when you don't have any free space, you are not going to have any alignment. Okay? So this beta is going to depend on the structure, how many monomers are in contact, these kind of things, and we have an answer for this. Yes?
Just a clarification. Is the P what was the N hat earlier? Is the polarization what?
B, this beta here.
P.
A P depolarization.
Yeah, is that N hat?
Yeah.
Okay.
Yeah.
So it's the same polarization, right?
Yes. There is another question on the back.
So that looks actually quite similar to another model which has been living in literature occasionally, where you orient with the force that's being exerted on you, so force alignment. Do you think it's similar? I
don't think it's similar. When you do force alignment, you induce a lot of flocking that you don't induce here. So possibly there is another mechanism that is induced flocking. Here is not, you're not inducing it. Okay, so now we introduce this regime. We have essentially already studied the case in which this tau c is very, very large, so the alignment plays no role. It's the case we have seen before, just motility. And now we're going to go to study the other limit in which this term is dominating, and so we can compare the two regimes.
So the deduction of free space, all these other deductions also were possible. For example, to the opposite direction. How do you choose which direction to take?
Yeah, so we only look, we did identify this vector, this RC, as the free space that is probed by the molecules that are here represented in orange, and they are not in contact. So this is the free space probed by the lamellipodium. Why we do that? Because SEAL, contact inhibition, is doing exactly that. The motion is induced only by the front, which for us would be the orange. Here is where you have protrusion extension, not on the back, only in the front. And during contact inhibition, only part of this protrusion extension is inhibited. Okay? So essentially we say, okay, you cannot move here, but you move in this direction. And what is the direction? Is the direction of the free space probed by the front. Okay?
Sort of closest to the earlier.
Yes, so it needs to turn slightly. That's the slide.
Primarily, it gave you the cells on the boundary, right? Because the cells on the bulb would have no such space.
When you, yes, you are totally right. So indeed, this is something that is coming from this beta. So beta is going to depend on how many neighbors you have. Okay? So if you don't have any free space, you're not going to have any alignment, right? Because you align toward the free space, there is no free space. So when you have no free space, this beta is going to 0. Okay? So when you study the phase diagram, what you find? Well, you start to see important differences. So again, what do we find? We found that while in the absence of SEAL we have a huge region of phase separation, in the presence of this contact inhibition, the region of phase separation is suppressed a lot. And so we can say that contact inhibition is promoting the homogeneous phase. So the critical point, if we want to use this terminology, is suppressed, and also the amplitude is the width of the consistence decreases. Or equivalently, we can say that contact inhibition is going to suppress density fluctuation. I'm going to go back to this point. How about the dynamics? So to compare the dynamics, what we do, what I'm going to show you now is comparing how the diffusivity varies as we increase the density along this line, so in the absence of SEAL, and this other line in the presence of SEAL. Okay? So we can see, is SEAL speeding up or slowing down the dynamics? And this is what you get. So this is the diffusivity in absence of contact inhibition, so the dynamics slowing down as you increase the density. When you switch on contact inhibition, you see that the red points are below the blue one. So the main message is that where contact inhibition is slowing down the dynamics. You see here we have a kind of weird kink, some strange behavior. So what's happening here is related to the question we had before, is that contact inhibition acts when you have free space. When you start to be very close to confluence, you no longer have free space, so this effect all of the point is going to vanish. So you expect that above confluence, the two diffusivities need to match. Okay? So this is why it's going up. So can we understand, I'm a little bit late, can we understand how to model this? And the main assumption is that, well, we can say that what's happened when you have a contact due to contact inhibition is that a cell is experiencing a contact and is turning. So contact inhibition is changing the rotational diffusivity. If you only assume that this is what is happening, so you don't assume that you have any change in the structure, then you can actually measure what is the typical decorrelation time for the polarity, and you can use this, and you say, well, the diffusivity in the presence of contact inhibition is the one you have in the absence of contact inhibition, but with essentially you are changing the rotational time scale. And when you do that, you get these points here, which somehow capture the typical behavior. So the main effect of contact inhibition is change in polarization time scale here. Okay, and how about the phase diagram? Well, it's easy to understand what's happening in some aspects. So for instance, in the absence of SEAL, if you consider the point A, you're going to see cluster. If you switch on contact inhibition, the polarity of the particle, which are represented by the color here, are not going to be random, but are going to be directed toward the free space. So if you start with a cluster, but all polarity oriented toward the free space, you're going to exert tensile forces on the cluster, and the cluster might break, which is what you see here. If you have, again, the consistent phase, but you are a high density, what you observe you have cavities in the absence of contact inhibition. Again, all the polarity are random. In the presence of contact inhibition, all the polarity points toward the free space. So again, you are trying to close the cavity, right? So you are trying to suppress density fluctuation. And so you put the tissue under tensile stress. And in this case, you're still in the equidistance region, so that these forces are not large enough to deform the cell and close the gap. But if you move to point C, that for some reason correspond to these things here, what you're going to see that in the absence of contact inhibition, you still have gap, but with contact inhibition, you close the gap. Okay? So it's promoting healing. And it's promoting healing. This means that it's changing the location of the confluence line. Contact inhibition is promoting confluence. And it's doing that by swelling the cell. Here we don't have reproduction, but you put the tissue under tensile forces, and because of this, you have a little bit of elasticity, and the cell can increase in size. And the typical change that we observe is below 7%, and this is similar to what you see in experiment when you suppress reproduction. Let me finish just mentioning wound healing and force chains. So one thing that you can do with this kind of model is to study force on the membranes, and this is, I guess, quite nice. So here, for instance, what I'm going to do is to color code the monomers according to the direction of the force of interaction of the monomer compared to the position of the monomer with respect to the center of mass. So essentially, the red means that the monomer is under tension. You're trying to locally swell the particle, where blue is under compression. And this is an animation of wound healing. So this it's a section of a very, very long channel, and there is no reproduction. So you're going to see wound healing only because the size of the particle are increasing a little bit. And you start with a condition which you see red and blue. So essentially, this is kind of zero pressure. There are no tensile stresses. And what's happened as time goes on, the cell on the boundary are going to polarize toward the free space. They drag the others. And everything is becoming, you go to confluence, and everything is becoming red, meaning that the system is suppressing density fluctuation and is putting itself under tension. Okay? So SIL is a mechanism that somehow tissue, they aid so much density fluctuation that, at least in this model, that they put themselves under tension to suppress them. This is what they are going to do, which is, of course, not standard. And this is the dynamics. Perhaps I can skip. Instead, I would like to say something about the forces. So you can also think about what is the force that one cell is exerting on the other cell. How do you do that? Well, you just sum up the force of interaction between the interacting monomers, right? And then you can think, okay, what is this force with respect to the line that is connecting the center of masses? And if you study the scalar product, you find that it's essentially is peaked at 1, -1, meaning that either you have forces that are parallel to the direction of separation or anti-parallel. So essentially, this is a to good approximation. You don't have frictional forces, which is similar to what has been reported by Corey. And this indicates that you can actually draw the forces as lines that are joining the center of mass, as so-called force chains, and to color code according to their strength, and the width here represents the strength, and the color represents the magnitude. And then you can study the distribution in different conditions. So here we're seeing what's happening before healing. We are in the red case. We have exponential tail both for strong repulsive and strong attractive forces, or after healing, we still have the same phenomenology, but with larger forces. So in any case, what I want to just to highlight is that possibly this model might open up a more detailed description of the mechanics of tissue. So I would like to close. And essentially what we have been doing here, we have introduced a model for cell and their interaction with a little bit of subcellular resolution. We model a little bit more precisely essentially the membranes. And what we have seen is that the key ingredient that gives rise to a new phenomenology in this model is contact inhibition of locomotion. It's a non-reciprocal sensing response. And what it's actually doing practically is opposing density fluctuation. You're trying to suppress density fluctuation, so this is very different from the usual motility-induced frequency variation. This is doing just the opposite. Perhaps I can take questions, if any. Thank you so much.
So is there a unique way to model CIL, or there are many options to model CILs?
So this is what we have been doing. So when the other way people have been doing is more like a kind of alignment interaction, but then you go into flocking. So when you do that, you find that contact inhibition is promoting motion in dense tissue, which is a bit weird given the name contact inhibition or locomotion, right? So this is the only way, yeah. So
It's very interesting. So I had a specific question. When you do you have to graph with the forces, where you define the forces between cells.
yes. This one?
The one before? No, the other way. That one, yeah?
Yes.
So usually you also get tension along junctions, so not with cell like this, but contractile.
Yeah,
Is
yeah,
this something that's possible in your model as well?
Yes, this of course, because this is a ring polymer. So we have the spring between the bits, so you can measure we are focusing on this essentially because this is novel. The tension you can measure and we can compare, but this is something that is not usually accessible in the other models. So this is why.
Yes, so I'd be interested to see, because you see often force chains along junctions instead of the way
And
you're
then
doing
following- yeah,
ortho earlier.
Yeah.
Have you
Something we
looked
can
at
do.
this?
No, we are not looking at this into details. Yeah, but we can do that.
Okay, sorry.
So there are some report that the wound healing dynamics sometimes depends on the geometry of the wound. Did you check any of those?
No, what I can tell you is that for sure you have different mechanisms. So this is what we have is wound healing driven by motility. In particularly in the embryonic state, this might not be the case. It's most like the tensional junction, the pull string mechanism that is driving the dynamics. So you may have different mechanisms that works in different contexts. Yeah.
And another quick question. So in the only one cell scenario, does the motility direction still changes there, or is it?
It's random diffusion.
Yeah, but that is random.
Random diffusion, random rotational diffusion. The standard.
This cell motions has this different kind of taxis. I mean, typically in like wound healings, I think like this galvanotaxis and these things matters. So here, these motions.
We are not introducing any gradient of anything. So this is just interaction. Yes.
Okay,
Yeah.
so like it's quite general. Like,
Yeah. It's quite. We don't introduce this. Yeah.
thanks.
Already too many things.
Okay, if there are no questions, let's start Massimo again. Okay, the next speaker is Aranyu. Aranyu will be speaking about active solids and some Aranyu?
Yeah.
I'll give you 5 minutes.
Thank you. Thank you, Arnob and Pinaki, for organizing this very interesting conference. It's broad, but not so broad that you can't understand half the talks. So I learned a lot, and so this talk will be very different from the other talks in the sense that there will be no simulations, no plots. Well, there might be one experimental plot from an experimental collaborator, but that's it. And okay, so basically what I want to convince you of is there are many kinds of active solids are actually like externally driven solids, and what I mean by like is that their long-time, large-scale hydrodynamic correlators of these two systems are the same. Hydrodynamics can only give you information about asymptotically small wave number and small frequency correlators. That's all hydrodynamics can give you, okay? And I want to convince you that these two can be similar, okay? So we all now kind of know what active matter is. These are particles, each of which have an independent access to some energy and uses that to do something, okay? Typically, we think of these systems as, sort of particles that have some internal batteries inside them, or, particles that can take up energy from an exothermic reaction that's being carried out in their environment, and you keep this exothermic reaction off chemical equilibrium by continuously supplying continuously supplying reactants and removing the products, right? But these are not the only kinds of active systems. So in fact, if you have any system in which you have a flux and you look at a plane that is transverse to the direction of the flux, the dynamics in that plane is active. And you can see that it has to be active by this definition, because every particle in that plane has an independent access to a free energy, energy because of the flux going through that surface, threading through that surface. And this is sort of my contribution to increasing the number of reviews in active matter. And there, sort of a large, so one very simple example of this kind of active system is when you have two bulk systems, when you have an interface between two bulk systems maintained at two different temperatures or two different chemical potentials. The 2D physics of particles or objects in that interface is active, okay? So then what is the fundamental difference between sort of a standard driven system like, a current carrying wire or a sheared fluid? So the difference is one of symmetry. So if you have an externally driven system, the drive itself breaks the symmetry of the system, whereas activity doesn't break a symmetry of the system. So here in the bottom, the systems are in green, right? So activity is not breaking any spatial symmetry in this plane, okay? That is a fundamental difference. And but if it has, and that matters a lot, of course. So you can talk about isotropic active matter, spatially isotropic active matter, but how can I talk about spatially isotropic driven system if I'm explicitly breaking a rotation symmetry there? I can talk about spontaneous breaking of rotation symmetry in active matter. How can I talk about spontaneous breaking of rotation symmetry in this kind of a system? Because I have already broken rotation symmetry. There isn't any rotation symmetry. So why am I asking this question at all? I mean, this question now seems kind of stupid, and the answer seems to be obviously no. So of course, driven solids and active solids should be different. So why am I asking this question at all? Well, the reason for this is something you kind of learn in high school. So, in high school, you sort of know about point groups of crystals. That means crystals break both translation symmetry and rotation symmetry. But you also know that crystals have sound waves, right? So sound waves or phonons are Goldstone modes corresponding to broken translation symmetry. And those are the only soft modes in your system, because if you had something else, you'd have to learn about them in school, because if you had other soft modes, they would couple with your phonons, and you'd have to learn about them in school. So what happened to the Goldstone mode of broken rotation symmetries? Where did they go? Yes? You had a question? So where did the Goldstone modes of broken rotation symmetry vanish? Well, they didn't vanish. What happened is they had become massive. And they became massive because of basically the Anderson-Higgs mechanism. The non-fancy way of saying it is that if you try to rotate a bit of the solid, you also stretch bonds. So think of a sort of a network of springs, okay? And now try to rotate a bit of that. So you always stretch bonds. But if you can take that spring network and you can push a bit of that network ahead without rotating anything. So rotation is always coupled to translation in a translation symmetry broken system. And it's easiest to do this, to see this actually not in a solid, but in this thing called a smectic. So a smectic is a Diedemann. So a smectic is a one-dimensional periodic structure in a d-dimensional system. So it's a periodic array of d-1 dimensional fluid layers, okay? And so where is the rotation symmetry breaking here? The rotation symmetry breaking is that you don't know what is the one direction that is being picked out. You could pick out any direction in space. You have the layers in one particular direction, and that's your rotation symmetry breaking, okay? And many smectics, but not all, are composed of sort of a periodic array of these kind of nematogen, so elongated molecules, which have sort of no correlations in space in d-1 dimension, but stack on top of each other. Okay, but this is so if they didn't stack on top of each other, this would have been a nematic. They would have some orientational order in space, but no translational order. And then you had a soft mode for those nematics, which is the director. Okay. So what this Anderson mechanism tells you, which is a fancy way of saying what I just said earlier, is that if you try to tilt these director fields, that corresponds, because of the coupling between the layers and the director, that corresponds to a tilt of the layers themselves. So delta n perp, which is the, which would have been the soft mode of a director in a nematic, is basically now proportional to del perp u, okay, where del perp u is the tilt of the layers, local tilt of the layers. But you know that in equilibrium, a free energy cannot contain delta n perp squared because of rotation symmetry. And because of this, because I told you that delta n perp is proportional to del perp u, now you know that in a smectic, a free energy cannot contain del perp u squared, which means a smectic cannot have a tension. So for the younger people in the audience, what would a similar argument in a solid tell you? Any takers? It tells you something about the free energy of a solid. What does it tell you? So what it tells you for a free energy of a solid is that the free energy of a solid can only depend on the strain tensor, on the symmetrized part of the displacement gradient tensor. Because you know that the curl of u in a solid is a rotation. Your free energy cannot depend on rotation. Okay? So yeah, so the upshot of all of this is that there is no massless orientation mode that's possible in any translation symmetry broken system. Okay. So, okay, how does, and by the way, I should, so this is basically the thing that will allow me to show that in many driven and active translation symmetry broken states, the hydrodynamics are equivalent, and this is a sort of a disclaimer. Only the spin wave dynamics, which means that I'm ignoring all defects, are similar. The defect dynamics is different, and I know it's different. Okay, and this is a really nerdy point about a particular system in which a particular case in which I know that defect dynamics is different. Okay. Okay. So okay, so let's first take the smectic and see why the driven and an active smectic should be similar. So this is actually a polar smectic. So delta n perp is del perp u. There is a force along the direction that these guys are pointing in. So the force is Fz, which is proportional to del perp n perp, which is del perp u squared. And if you have a driven smectic, the argument that I used for rotation invariance doesn't work anyway, so you again have you have no invariance under tilt, so you get a force density which is proportional to del perp squared u. So this is, in both of these cases, you see that you have a tension that has emerged. Okay, so in both an active smectic and in a driven smectic, there is a tension. Okay, in an equilibrium smectic, there is no tension, and the smectic is polar, so there is no n going to minus n symmetry, so it's moving in the direction it's pointing in. Okay. Okay, so let's write down the hydrodynamics of this object. So first let's look at the hydrodynamics of driven smectics. This appears and this was, looked at years ago in the context of charge density waves in superconductors, etc. So this is an anisotropic KPZ, and I'll come back to this. And if you have a polar smectic, and basically I have gone into the co-moving frame here. If you have a polar smectic, you have a very similar equation, except that I have not, so here, even here there was a term which was like lambda 0 del ZU in the driven case, but I absorbed that into a redefinition of the direction of motion, of a coordinate. And here, the only distinction between an active and the driven smectic is a relation between lambda 0 and lambda perp. Okay. But this is actually immaterial for hydrodynamics of the system. And that's because, as I have done here, I can also reabsorb lambda 0 in a redefinition of Z, where Z is the direction of motion. Okay? So I can redefine Z and completely eliminate lambda 0. And then you can see that this equation and this equation are exactly the same. And people have looked at the flow, the properties of this, actually from a long time ago, actually. This used the flow diagram was from 1990s, and what you know is that if lambda perp and lambda z have opposite signs, the nonlinearities become irrelevant. If they have the same sign, it basically becomes a KPZ and you don't have a fixed point. That's what you know. Okay. Well, but okay, why were they equivalent? They were equivalent because I could remove lambda 0 altogether by a redefinition of Z, right? If I have a quench disorder in the system, if this xi here is not an alleled noise but a quench noise, then I cannot do that rescaling. This rescaling, don't want to set up a TV. This rescaling depends on there being a convenient delta function in the correlation of this noise. So if I cannot do that rescaling, what happens? Then is an active and a driven smectic distinct in the presence of quench disorder? Well, let's see. So now I'll go specialize to 2 dimensions. Just for simplicity, there is no particular reason I can do it in arbitrary dimensions. So now now lambda x, which was lambda perp earlier, because it was in d minus 1 dimension, has to be fixed to lambda 0 over 2 due to rotation invariance. But notice the structure of this equation. So there is a lambda 0 del ZU, and because of the presence, so I want to first look at the static structure factor of this, the equal time correlator, so the static properties. And because you have a lambda 0 del ZU, you can immediately throw away the lambda z del ZU squared and kz del Z squared U, because they have high orders in gradients. And I'll show you post facto that everything still remains consistent. Okay? So if I throw those 2 away, then what I get is this equation. This is a 1 plus 1 dkpz, whose exponents I know. And more importantly, the lambda x over lambda 0, which is the coefficient of this guy, is not renormalized. So though the lambda x over lambda 0 is fixed by rotation invariance here and is not fixed by rotation invariance in a driven system, in neither case is it renormalized. So because it's not renormalized, the fact that it has a particular value does not change the scaling at all. In both cases, I have the same exponents as the KPZ, 1 plus 1 dimensional KPZ. That is, the dynamical exponent becomes the anisotropy exponent here, and the roughness exponent is the roughness exponent. Okay? Yeah. So the constraint of rotation invariance doesn't matter. And then you can basically use these exponents to check that the thing I did, which was dropping del Z squared U and del ZU whole squared, is okay, and it all works out fine. Okay, good. So that's for the smectic. So I have shown you that a smectic, A driven smectic and a polar active smectic are equivalent both in the presence of annealed noise and in the presence of quenched noise. Okay? Now let's go to a solid. Okay. So you can have a polar solid in which you have a bunch of a crystalline state in which every particle is a polar particle and it's moving in the direction it's pointing in. And you can have a sort of an externally driven two-dimensional crystal. Okay. And the dynamics of the externally driven two-dimensional or three-dimensional crystal was discussed years ago by Lahiri and Ramaswamy. And this is relevant in multiple contexts. It's relevant for crystals that are sedimenting under gravity. It's relevant for vortex lattice arrays in superconductors that are moving because of driven vortex lattice arrays, etc. Okay? And these equations are actually interesting, quite interesting in themselves. So you can immediately work out the eigenfrequencies of this, and you'll notice that if alpha 2 and beta 2 here are greater than 0, you get a sound mode without inertia. This is a non-reciprocal system. This was years before the word non-reciprocal was used in this context, but this is a non-reciprocal system. If you have, if alpha 2 and beta 2, this product is less than 0, you have an instability. And the point between where you go from the stable solid with sound modes to an instability is an exceptional point, and the physics of that exceptional point is actually quite exceptional. It's basically, this is Dibyendu Das and Mustansir Barma looked at this years ago, and Satya Majumdar during his PhD looked at this again years ago. Okay? It has something called fluctuation dominated phase ordering, etc. I'm not going to go into that. Today I'll always remain in the regime where the solid is stable. Okay. So then, sort of 20 years after this, we wrote down the hydrodynamics of active solids, and it looks very similar to the driven solids, except that now beta 1 and beta 2 are related. Okay. But again, this doesn't matter for the hydrodynamics, and you can see that by noticing that I can again completely eliminate beta 1 in both cases by redefinition of Z. And that changes alpha 1 as well, but alpha 1 is arbitrary. Alpha 1 is not fixed by rotation invariance. So the hydrodynamics of both of these systems remains the same. Okay, but again, what happens with quench disorder? I can't do that rescaling if I have quench disorder. Well, again, let me go to 2 dimensions, because 2 dimensions is the case that's interesting. And so you have this set of equations, and you can immediately calculate the static structure factor. And you notice something. You notice that you need alpha 2, beta to be greater than 0. You need this condition for stability. And then you notice that as long as alpha 1 and beta 1 is negative, this coefficient, this denominator, cannot vanish for any value. Right? If this denominator cannot vanish, then you see that for all directions of wave vector space, uz squared and ux squared average scale as 1 over q squared, where q is, so I should have mentioned that q is the wave number, okay? And then you can show that if it vanishes as 1 over q squared, there is no relevant nonlinearity in the problem. You cannot cook up a relevant nonlinearity here, okay? And again, there is the relation between beta 1 and beta 2 doesn't matter in any of this, okay? You have a more interesting case when alpha 1 and beta 1 is greater than 0, and then, this object, the denominator, vanishes for some value of qx and qz, right? So there is some direction of wave vector space in which the denominator vanishes at this order. So you need a next order guy in the denominator, okay? And it vanishes precisely because, that is the direction in which the sound speed vanishes. So what is the sound speed doing first, physically? If you have a system with a quench disorder, but you're moving with respect to the quench disorder, then the quench disorder, from your perspective, looks like an annealed disorder. There's no difference between a quench disorder and an annealed disorder, right? If you're running past an arrow that's pointing in some direction, you've forgotten about the arrow after some time. Okay. But a fluctuation moves with the sound speed. If the sound speed vanishes for certain fluctuations, that means for those fluctuations, a quench disorder is like a quench disorder. And therefore, in those specific directions, uz squared and ux squared scale as 1 over q to the power 4, not as 1 over q squared. And then there are relevant nonlinearities for gradients in that direction. And I don't know much beyond that here. I couldn't do the RG. I tried to map it to the Ettas and Kardar equations, but I've not managed to do it till now. But importantly, there's still no distinction between an active system and a driven system, even in this case. Okay. Okay, good. So I'm not sure whether I'll talk about this. Okay, let me quickly talk about this. So you remember, the idea that active systems and driven systems are the same came in because the rotational Goldstone mode was massive. So if I don't make it massive, which is illegal, but let me indulge me for a second, if it is not massive, then they should not be the same. And indeed that's the case. And I would never have done this usually, but what happened was Benoit Ledoux had this experiment on cell layers. And puzzlingly, what happened, what it looked like was that the cell layer was very solid. There was no neighbor exchange for days actually. This experiment goes on for like 2 days. But when they measured the velocity correlators or the polarization correlators, they found that the polarization correlators are not massive. Okay, I mean they have a decay, right? Which means that those correlators scale as 1 over q to the power q to some power. Okay. The orientational correlation. Okay, sorry. So let me actually say something more. So if theta was massive, then 1 over q to the power 0, then it scales like, it goes to a constant. Over q to the power alpha. Okay. Yes.
The cell orientation or the cell polarization or all of the above?
Sorry.
Sorry, I'm not sure. Can you distinguish between the cell velocity, the cell possibly orientation or polarization, and the motility direction? Which one do you mean
So
here?
it's they measured cell velocity and the polarization, which was the apical basal sort of shift. So if you look at every cell, there's a sort of shift between the top and the bottom. They associated a pole vector with that. They measured that as a polarization, and they measured cell velocity. Both of them have a decay of this sort. Okay. So, okay, this was puzzling because I would have expected theta squared to look like this. Yeah, I don't need the. And of course, this cannot be true at arbitrarily large scales and long times, because at arbitrarily large scales and long times it should go back to what I was talking about earlier. But it can be possible at intermediate length and time scales, because you have a theta dynamics of this sort, and when this time scale, for time scales smaller than this, or length scale smaller than this, the theta dynamics essentially remains massless. What that means is I've actually illegally switched off effectively a coupling that is required by symmetry in my free energy, okay? And that coupling is relevant. So if that coupling was switched on, I'll move away from this fixed point, okay? So, okay, then after doing that, I can write down the theory again. I can do a nematic and a polar version. Let me not go through it. Actually, let me. So what's the theory? The theory is that you have a velocity that's proportional to some polarization. So you're moving in the direction you're pointing in, and you have a polarization that does its own thing essentially. Okay. In the polar case, you have this because you actually eliminated this. So this is the lowest order invariant possibility. Okay. And if you do that and write these equations down in a polarized state, what you get is ux dot going as theta, where theta is the angle, and theta dot basically going as del squared ux. What you can immediately see from here is that the ux and theta beat against each other to give you a wave. Okay? It gives you a sound wave. And the thing in nematics is similar but not the same. I'm not going to talk about it. Okay? So it gives you a sound wave. Then you can basically immediately calculate that the displacement fluctuations are huge, enormous. Okay? Which means that basically if this were true at large enough scales, the tissue would be destroyed. Okay? There could not be a solid. So, and the important point for my sort of what I'm trying to establish is that if I had this solid in an external field, there would not be any 1 over Q4 divergence. The theta field would relax fast to the driving direction. Okay, so this divergence is a signature that the free spin solid is not like an externally driven solid, and the precise reason being that it has a free spin. Okay, good. So, and now I'll go on to three-dimensional solids, and before that I need to give you a little bit of background on what is called a liquid crystalline elastomers. Liquid crystalline elastomers are basically isotropic solids in which there are elongated objects which can spontaneously order. So that ordering breaks the symmetry of liquid crystalline elastomers. So in the reference state, these are isotropic. In the target space, they're anisotropic. Okay, and you can see that basically it can align in any direction you want. So if I had if it could align in this direction, I could rotate it, and it could align in a different direction. And those two states are configurationally different, but energetically the same. So you can go from this state to this state in a liquid crystalline elastomer without costing any energy. Okay, what that means is I can shear the nematic elastomer, and the cost of the shear can be made to vanish by the director field reorienting. Okay. So these liquid crystalline elastomers are sort of funny objects. There is no cost for a WZ perp shear, and these are a sort of a weird cross between a sort of a smectic system and a columnar system. A columnar is a crystalline array of liquid columns. So if you look at the Z direction, the displacement field along the ordering direction, that looks like a smectic. The displacement field transverse to the ordering direction look like a columnar. Okay, and an active liquid crystalline elastomer has an additional stress which basically end up looking like a active cross between an active columnar and an active smectic. The point is, again, whether I have an external field or I have an activity, it doesn't matter for this. Let me go over this quickly. Let me not bother about this. Okay, so now what I'm going to talk about. Oh, sorry, I needed to say one thing. Yes, 5 minutes, okay. Liquid crystalline elastomers have a higher symmetry than usual. It has an OD cross OD symmetry. So usually if you have a solid, it has a symmetry under rotation in space. This has a symmetry under independent rotations in target space and reference space. So it has a higher symmetry, okay? So that will matter. That's why I wanted to point that out. So now let me consider a liquid crystalline elastomer moving in a three-dimensional system, three-dimensional external medium. Okay, so it's a frictional medium. A liquid crystalline elastomer is trying to move through that. Okay, So I can write down the hydrodynamic equations for this case. I can write down basically to first order gradients. I can write down a velocity. I can construct a velocity. Turns out that this chiral term here actually does not contribute in the elastomeric state. So I get back the equations of the driven solid I flashed at the beginning of my talk. Okay? And this is really a consequence of O3 cross O3 symmetry of elastomers. What that means is this set of equations can be stable, because I showed you that this is stable in the earlier part of my talk. However, now let's consider a chiral elastomer moving in an external, active chiral elastomer moving in an external anisotropic medium, or a chiral elastomer driven by a field of some sort. Okay. So I can consider a polar field or a nematic field, or I can consider a polar anisotropy. All of these cases actually look very similar. I can construct this, and then let's not bother with the algebra. Importantly, what I get is that the eigenfrequencies have this structure, which means that this object is generically unstable. So here is a huge difference between a nematic, a chiral elastomer, chiral active elastomer, and then a chiral elastomer in an external medium, external field. A chiral elastomer in an external field is always unstable. It cannot exist, whereas a chiral active elastomer can exist. It also means that if you have a sort of a chiral tissue or a chiral cell layer moving through an external medium, that object, a three-dimensional chiral tissue moving through an external medium, that object is always unstable. It always has a specific size. It will break up after that. Okay, and you could have a nematic anisotropy and it would still be unstable. Importantly, you could have any anisotropy and it would still be unstable. So basically, if you have an external reference, rotating with respect to that reference is not a symmetry, right? So you can have a force density proportional to curl of u, which is the rotation with respect to a medium. But if you have that, you can immediately see that you have an eigenfrequency. I mean, this you immediately can solve, and you can see that you have an eigenfrequency that is unstable for, you have a pair of eigenfrequencies, one of which is unstable. Okay. So what that means is that, as I was saying, three-dimensional chiral active solids don't exist in an anisotropic medium, or three-dimensional chiral solids that are externally driven don't exist, whereas three-dimensional externally driven, three-dimensional active elastomers can exist. So that is a distinction, and that distinction is a consequence of O3 cross O3 symmetry of elastomers. So it's a consequence of an extra symmetry beyond the sort of usual symmetries of a solid. Yeah, I'm done actually. So in fact, actually, if you had a real solid, so first of all, experimentally, elastomers are actually almost never available. Disorder makes the O3 cross O3 symmetry go to an O3 symmetry. And if you have that O3 symmetry, I can show that that is also unstable. So an O3 solid, a polar solid is exactly like an externally driven solid. Polar active solids is like an externally driven solid. An elastomer is slightly different. So that's the only case I know where it's different, okay? Okay, so to summarize, what I've told you is that achiral solids are like externally driven solids in the presence of both anneal and quench noise. Chiral elastomers are different, but only because of the O3 cross O3 invariance. And spectacularly, chiral elastomers in an anisotropic medium, chiral active elastomers in an anisotropic medium are generically unstable. Okay, so and this instability is not a consequence of what is called odd elasticity, but odd mobility. So yeah, okay, and these were the people with whom much of this was done. And thank you. Yeah. Bye.
Great. Questions?
In the slide where you showed experiments on motile cell layer, you mentioned that they are very rare neighbor exchange. So, so is it like a solid flock?
Yeah, it is a solid flock. That's the whole point. It's a solid flock, but I told you just to start with that in a solid, the director fluctuations are always massive, which means they're always of that form. Theta squared goes to some constant at small q. Here, they measured theta squared, and they found that it doesn't go to a constant, it diverges at small q, okay, small wave numbers. That was the puzzle.
So is there any transition from the disorder to the solid flock, or?
How do you do the transition? I mean,
Like
there can be it is
plot,
confluent, it's a confluent cell there. You cannot create, I don't know how to experimentally go across that transition, except by increasing the density.
If you plot an order parameter and see that the system indeed goes from some disorderness then to the solid flock.
So as that, okay, so in time, as the density increases, it indeed goes from a disordered to an ordered state, but that's just because it's getting more and more confluent.
Okay, thanks.
Yeah.
Yeah, to follow up on that, so sorry, I have a hard time thinking in hydrodynamics. So what exactly does it mean they're not massive? So say I get some data from experiment or simulation, it's flocking, it's solid, it's not rearranging, and I can think of at least 3 different microscopic interactions which are going to give me this.
Yeah.
So what is this telling me? About what's happening locally?
It's not telling you anything about what's happening locally at all.
But
So
there should be a map between, say, coarse graining my local interactions, should give you hydro equations eventually, right?
yes, so the point is the hydrodynamic equations will always, okay, if you really coarse grain a microscopic model to really large scales, you will get the dynamics of a solid that I showed you previously. Okay, so in that dynamics of solid, there is not going to be a soft mode for display for orientational fluctuations. The point is, you have a coefficient in that. So when you do the coarse graining, you will basically get an equation for the angle field of this form. Okay, and the point is this angle field. Sorry, oops. This is supposed to be good, but it's okay. See, this is a time scale, inverse time scale, right? If you are below this inverse time scale, this term doesn't matter compared to whatever else there is in the equation, right? So if this term doesn't matter, the other terms, so basically you can be in a regime in which this other terms dominate over this term. At the small time regime, this term will always dominate, but you can be in a time window in which other terms dominate over this. That's all I'm saying. The microscopic theory, microscopic mechanisms will give you this in some form. The values of C, the values of gamma, etc. will depend on microscopic parameters. But that's the only thing that will depend on microscopic parameters. The form will not. Okay.
Okay, any other questions?
Good.
Okay, if there are none, then let's thank Ananya again.
Yeah.
Yeah, we bring coffee and